In this video we're going to explain the Lotka-Volterra equations. The idea here was, we've got some lagoon or something, and there's some fish in it and some sharks. The number of fish is going to be called capital F, and the number of sharks is going to be called capital S. And these are going to change over time according to these equations, the Lotka-Volterra equations. They depend on some parameters, alpha, beta, gamma, delta. We're going to use, for this picture, we're going to use these particular values. Alpha is 10 to the minus 2, beta is 10 to the minus 4, gamma 10 to the minus 1, delta is 10 to the minus 5, but you could choose different parameters. And the equations are like this. So F dot is alpha F minus beta SF. So what's going on here? Right? I mean, the idea is that the fish are reproducing. If you didn't have any sharks, if S was 0, then you would just have F dot is alpha F. The more fish you've got, the faster they reproduce, and you get kind of exponential growth of the fish, at least for some reasonable approximation. But if there's sharks around, then of course they're going to be eating the fish, so that's going to reduce the effective rate of growth of effective reproduction rate of the fish by a factor beta S. So you've got alpha F minus beta SF. Or alpha minus beta S times F, if you like. So the fish are reproducing at a rate alpha minus beta S. Okay. Well, the sharks, on the other hand, if there's no fish, so if F was 0, then of course the sharks would not have anything to eat, and so they would start dying off. You would have the rate of growth of the shark population would be like so we have negative constant times the number of sharks you've actually got. So you'd have like S dot is minus gamma S, and that would have like S being constant times e to the minus gamma t. The population of sharks would gradually die out as they all start. But of course, if there's fish around, so the sharks can eat the fish, then the sharks will be healthier and happier, and they'll successfully reproduce. So here you've got S dot is minus gamma S plus delta SF, or if you like, it's delta F minus gamma times S. The rate of reproduction of the sharks is delta F minus gamma. So you've got plenty of fish, then the sharks will reproduce. So if you don't have enough fish, then they won't. So that's how you should think about these equations. And we're going to sort of examine the solutions in terms of the so-called phase portrait. So you've got this diagram here. The horizontal axis is F, the number of fish. The vertical axis is S, the number of sharks. And so we put a little point on this phase plane, and we see how it evolves. So at the moment here, the numbers are given like this. There's 12,000 odd fish and 51 sharks. So in other words, our horizontal and vertical axes different scales here, because number of fish is always going to be much bigger than the number of sharks. So but number of fish is 12,000 or so, and if we carry on a little while, then the number of fish now is increased as we move to the right, because the horizontal axis is the number of fish. So as the number of fish increases, the point moves to the right. And the number of sharks, it was 51 a minute ago, now it's increased to 63. It's gone up a bit. So the vertical axis is S, the number of sharks. So increase in the number of sharks corresponds to our point moving upwards. Okay. And now we're so we look here. Now we're in this range here where there's lots of sharks. Okay, we've moved up quite a bit. There's lots of sharks. So the sharks are eating lots of fish, and so the number of fish is decreasing. Right? So number of fish is decreasing. That means our point is moving to the left along this. So our red line, the red solution curve, is sloping up to the left here. And the numbers are given here. F dot is minus 99 or so. F dot is negative because the number of sharks is decreasing. But S dot, the rate of change of sharks, that's positive. The number of sharks is increasing because we've still got plenty of fish. Okay? And if we just carry on a little longer, but now we've got over to this region here. So we've got we've got fewer fish. More of the fish, we move to the left, the number of fish has decreased because fish have been eaten. And now, because we've got fewer fish, you've got not enough fish to feed the sharks, and so the number of sharks is decreasing. S dot is negative now because there's too few fish, the sharks are starving, and S dot is negative. And F dot is also negative, right? There's still got, although the number of sharks is decreasing, there's still quite a lot of them, and they're still eating lots of fish, and so the rate of change of the fish is negative. Now we carry on a bit further. Now we've kind of population crash of the sharks. There's rather few sharks now, and so they're not eating the fish, and because the fish aren't being bothered by the sharks, the number of fish is increasing. So our point is moving to the right as the number of fish increases again, but still, even though the number of fish is increasing, it's still quite low, and so the sharks don't have enough to eat, and the sharks are still dying off. We're still having a negative rate of change of the sharks. Now we've got to here, the number of fish has increased quite a bit now, and so now there's enough fish for the sharks to eat, and the shark population is increasing again. And we let this run; it just goes in cycles. We get explosions of the fish, and then explosions of the sharks, and then they've got too many sharks, and they eat fish. Fish population crashes, and it all goes around in a cycle like so. And you see you've got these kind of concentric curves, and if you go here, with we've got around 10,000 fish and around 100 sharks, then the numbers only fluctuate rather little. You don't get you just get minor fluctuations here. Everything's become quite stable. And if we go right in the middle here, if we had precisely 10,000 fish and precisely 100 sharks, then nothing would change at all. Everything would be completely stable. But we didn't quite click in exactly the right place, so this point is moving around in small circles around that equilibrium point. Rate of change of the sharks is really quite small. Rate of change of fish is quite small. Everything is changing rather slowly as we just oscillate around this stable point here. So that's roughly how the Lotka-Volterra equations work. If we start a long way away from the equilibrium point, then we get these kind of wild increases and decreases in the population of both the fish and the sharks. But if we start close to the equilibrium point here, then nothing much changes.